We are pleasure to present our search in Indonesian Journal for Electrical Engineering and Computer Science. The title of our paper is An Efficient Frequent Itemset Finding in Distributed Datasets with Minimal Communication Overhead. Table of Contents contains introduction, model of communication, proposed approach, result and discussion, and finally conclusion. Distributed data mining employs a range of fast, parallel, and distributed techniques to uncover implicit and valuable knowledge. One of the most prominent techniques is association rule mining, which aims to identify significant relationships between attributes within the database. The generation of frequent item sets is a fundamental and essential step in solving the association rule mining problem. The Apriori algorithm introduced by Agrawal is a foundational and pioneering algorithm for mining frequent item sets in transactional database. The general concept of this algorithm involves iteratively scanning through item sets level by level. At each level k, a set of candidate item sets of size k is generated by joining the frequent item sets identified in the previous iteration. This set of candidates item sets is then pruned based on the statistical metric called support. Many distributed algorithms have been developed for frequent item sets mining in distributed environments designed to provide substantial computational parts, include CD, conditional distribution, distributed mining algorithm, fast distributed mining, optimized distributed association rule, distributed decision miner, these algorithms, which utilize the determinate parallelism paradigm, differ in their techniques for pruning new candidates or whether they employ candidates containing techniques. In contrast, algorithms based on task parallelism, such as data distribution, intelligence data distribution, and hash-based parallel mining of association rules, and others. In literature, many approaches focused on improving distributed algorithms for mining frequent item sets in distributed environments. Our work is concerned with the search for frequent item sets in order to propose new solutions and design a novel algorithm called finding efficient distributed frequent item sets well adapted to distributed environments by improving performance. This approach aims to address the challenges identified in existing distributed algorithms. The focus is on reducing communication and synchronization costs between different sites, which are critical for evaluating the performance of distributed algorithms. The work contributes to minimizing data scans by reducing the number of candidates generated for global information computation in distributed setting. We propose adapting the master-slaves model to significantly reduce the number of communication and synchronizations between sites, thereby minimizing redundant calculations for candidate item sets. The master processor segments an OTR database into clusters and assigns these clusters to slave processors. The master sets coordinated between the slave sets, reducing the number of messages exchanged during each iteration k. The slave sites send messages to the master sites, which then replies with messages to all slave sites. Our algorithms consist of two fundamental phases. The first phase is master sites partitions the horizontal database across all sites equitably by dividing the number of transactions by the number of sites. The execution phase begins with converting the horizontal database into a vertical data format for each slave site, generating a list of sites for all item E. This method involves a single pass through the horizontal transaction database to identify the transaction seed for each item E, which is then used to construct the vertical the transaction database. For example, figure below illustrated the conversion of two slave sites in a vertical transaction database. Figure below illustrates the conversion of two slave sites in a vertical transaction database. The first technique established the counted list data structure for each slave seed to facilitate the computation of frequent one item sets and two item sets using a two-dimensional matrix of size where M represents the number of items in the vertical transaction database. The counted list data structure is employed to optimize the support calculation of candidate item sets without accessing the vertical database. The matrix provides a projection of the vertical transaction database for each slave site. Figure below illustrates the construction of the counted list matrix for slave set 1 and slave set 2. The master set then constructs a global structure by summing the supports from the reference slave sets without needing access to the vertical database or additional communication with the slave. The second technique of our algorithm aims to identify this set of k item sets, k superior of 3 within the slave set database. To generate candidates item sets node for the next level, the algorithm employs a subjoin of the k item sets generated in the previous level. The algorithm determines the teeth of k plus 1 item sets by intersecting the teeth of the two k item sets that share the same items. The algorithm continues to construct nodes at each level along with their teeth until no further nodes can be generated. The approximate support of the set of candidate key item sets is determined by counting the size of the seed set for each node generated in the tree structure. The figure below illustrates the second technique using the previous example from database. The third technique is necessary to validate the support values. Our algorithm aims to determine the exact support of the k element sets by focusing on transactions that includes the subset of the k item sets identified in the previous iteration that contain the minimum supports. This method significantly reduces the number of transactions required to accurately determine the supports of the item sets. This method, our refinement techniques, scan the database only for transactions associated with the subset of an item set that have the minimum support threshold. This method significantly reduces the number of database accesses required to identify frequent K item sets. The proposed method is illustrated in figure below, which details the methodology employed by our algorithm and its K components. We present the results and discussion for of the performance of our algorithm. We evaluate the algorithm using two datasets from FEME. The experiments were conducted in a distributed environment using a master-slave scheme where datasets were partitioned horizontally across multiple slave sites. The primary objective is to assess the efficiency, scalability, and communication overhead associated with our algorithm and how these aspects compare to those of the Apriori and CD algorithm. For the cheese dataset, the results depicted in figure below also indicates that our algorithm outperforms the other algorithms. Also, the other datasets as shown in figure below, our algorithm consistently outperformed both a priori and CD algorithm across all support thresholds. The scalability of our algorithm with more slave nodes is figures below the AMPA of node increase and the convergence at high node counts. The results of the study highlight very important insight about our algorithm and its performance in distributed context, efficiency gains, superior scalability, implications of finding. Our results, the proposed method algorithm addresses this limitation by reducing the number of candidates, item sets, and communication phases required to generate frequent item sets. This is especially critical for large datasets where communication costs can become a major bottleneck. The reduction in communication rounds observed in our experiments mirror similar improvements reported in other research on distributed frequent item sets mining. The experimental results strongly support the conclusion that our algorithm offers substantial improvements in both efficiency and scalability compared to the traditional a priori and CD algorithms. Its ability to reduce communication phases while training high performance across varying datasets, size, and numbers of slave nodes position it as a highly effective and solution for mining distributed frequent item sets in large-scale data environments. Our study demonstrates that our algorithm is more resilient than a priori and set algorithms and confirms the main rule of using the master sets with the proposed techniques of effective validation of results at each iteration of obtaining frequent K-item sets. The future studies may explore the problem of mining distributed association rules within a distributed context. The goal is to propose new solutions and design a novel algorithm that is well adapted to distributed environments based on our algorithm. Our studies, our study demonstrated that our algorithm is more efficient and also our finding provide conclusive evidence that this approach is more efficient and effective than other distributed algorithms a priori and CD regarding the number of candidates item sets generated where data is distributed across different sites by reducing communication and synchronization costs between sites. The proposed method in the study employs a master-slave communication model distinction between a master set and multiple slave sets we found, and the model significantly reduces the communication and synchronization costs required for distributed global frequent item set computation compared to the communication scheme using in previously presented parallel and distributed algorithms. Thank you.